This is the September 2025 NASA Night Sky Network member webinar. If this is your first time joining us, welcome. We have these every month, and you're welcome to join us here on YouTube. Or if you're a member of an astronomy club, we encourage you to find your local astronomy club. There are about 400 of us across the country, probably one very near you. So tonight I'm hosting your webinar. I'm Vivian White from the Astronomical Society of the Pacific here in San Francisco, California, and I am super excited to introduce our guest speaker, Rebecca Robinson from the SETI Institute, who's the outreach lead for NASA's MUSE mission. But before I get started, I want to go ahead and turn it over to Kat for a couple of quick announcements.
Hi, everybody. So welcome to the September webinar. I do just want to make sure that if you are joining us and you haven't been able to attend some of our previous social hours, we will have an NSN social hour on October 8th. That is going to be at 8 p.m. Pacific time, and I'm going to go ahead and post the link here in the Zoom chat so that you have a chance to join. It's open to all NSN members, and we're just going to, it's a super informal hour-long chat where we all just, connect and talk about things that we have going on. But the primary topic of discussion will be the NSN updates. That email went out on September 1st, or actually just around September 1st. It was a little bit after, but the key topic will be about these updates. And if you haven't had a chance to, take a look at some of the updates, I'll go ahead and post that link here in the chat as well. And this just pertains some of the things that we offer, such as Night Sky Notes and the materials that we send to clubs. So I really want you all to go ahead and just take a look at that and make sure that you join us for the social hour. And one more thing before you go. We do have International Observe the Moon Night happening on October 4th. And so if you haven't had a chance to register for that event, you can go ahead and register on NSN as you typically would when you add your events to your calendar, or you can register with International Observe the Moon Night directly. And I went ahead and I posted that link in the chat as well.
Thanks, Kat. It's great to see so many of you joining us tonight. For those of you who are joining us on Zoom, you can find the chat window and the Q&A window. Many of you have already found the chat, but if you have questions for our speaker tonight, go ahead and put that in the Q&A window. Sometimes it's under the more ... at the bottom of your desktop window. Feel free to say hi to each other in the chat, but you can also let us know if you're having any technical difficulties there. But just so we can keep track of the questions and don't lose them along the way, feel free to put the questions in that Q&A. You can also send us an email anytime tonight at nightskyinfo@astrosociety.org, and we'll throw that in the chat as well. All right, so I'm going to go ahead and hit record, and we're going to get started. Oh, you're already recording. Great. All right, then I'll just get started. Welcome everyone once again to the September 2025 NASA Night Sky Network webinar. I am so thrilled to have one of my favorite people around, Dr. Becca Robinson, who is a solar scientist, a world traveler, a rock collector, aurora chaser, a stargazer, and last but not least, the outreach lead for NASA's upcoming Multi-slit Solar Explorer, or the MUSE mission. Whether she's greeting visitors at Badlands National Park or cruising through the Norwegian Arctic, she enjoys spreading the beauty of solar science everywhere she goes. Becca received her Bachelor's of Science in Physics and in Astrophysics from Michigan State University, her Master's of Science in Geophysics from the University of Iceland, and her PhD in Theoretical Astrophysics from the University of Oslo. As you can tell, she is well-traveled, and she's got a great presentation for you tonight. I love listening to anything that Becca says. Please welcome Dr. Rebecca Robinson.
Thank you, Viv. All right, I'm going to go ahead and share my screen optimized for video. Let's see how this looks. How are we looking to you?
Fabulous. That's a nice big prominence.
That would be, yeah, so that's a non-eruptive flare. These are real observations from the Solar Dynamics Observatory. And I wanted to warm you all up a little bit with some of these really beautiful multi-wavelength, which in the case of the sun means multi-layer observations of the sun. Here we're seeing some flaring ribbons here. Those are about to get pretty bright and pretty energetic there as they interact with one another. But this is the subject of my life's work. This is the subject of what I do and what I have done for a while. There's some coronal rain there. Did you know it rains on the sun? But maybe not the rain that we're used to. So I'll just bring us to my title slide. It's very busy, but a lot of funding went into this work. So I want to make sure to give everyone credit where credit is due. But this is what we're going to talk about today. We're going to talk about the sun. We're going to talk about the Multi-slit Solar Explorer, which is one of NASA's upcoming heliophysics missions. And we're going to talk about some of my work that led me to this place. Viv already gave me a really fantastic introduction, but to repeat that, I am a Michigan girly. If there are any Michigan gals or guys out there, or anybody in between, hello. Happy to always meet Michiganders everywhere I go. My master's degree was in geophysics, particularly in glacial flow models. And so that's why you see this very strange picture of a heliophysicist drilling an ice core, not normal in our line of work. But it was during my master's degree, learning a lot about glaciers and how different climates impact the flow of Icelandic glaciers. But what I really wanted to do was learn about the sun's magnetic field. And I got that fantastic opportunity in Norway, where I did my PhD, using solar simulations of the magnetic field. And we're going to talk about that a little bit later. But I have done a lot of outreach as well. Some of my outreach adventures include sailing up and down the Norwegian coast, as Viv said. I was one of the lucky ones who had an outreach requirement during my PhD. So I got a full year of funding to do basically whatever I wanted as long as it pertained to outreach. And so I made a deal, of course, with a cruise ship company and sailed on board as the onboard expert in the sun and northern lights. And as you can see, we had some really spectacular displays. Some of you might have caught northern lights over the past few nights because we've had some interesting space weather this week. But I've also worked stateside in outreach. After I finished my bachelor's, I worked at Badlands National Park as their resident astrophysicist. And that meant that I gave evening programs and night programs where we'd pull out the telescopes. But it also meant that I worked during the day pulling out the solar telescopes. And this lovely red circle here in the image is a hydrogen alpha view of the sun. I'm sure some of you are familiar with that, with a couple of prominences here sticking out of the sun. So that was really lovely to see there. And I will mention, along the lines of national parks, we will be at the Death Valley Dark Sky Festival this upcoming February. So if you are interested in coming to Death Valley during a month where it's a little bit less death, please join us there. We will be there with the SETI Institute. And speaking of the SETI Institute, all of this outreach work has informed what I do today. I am the outreach lead for NASA's Multi-slit Solar Explorer, and that outreach program is headquartered at the SETI Institute. The MUSE mission itself is headquartered at Lockheed Martin's Solar and Astrophysics Lab in Palo Alto, California, but our outreach department is headquartered just down the road a few miles in Mountain View at the SETI Institute. We have 3 local Bay Area partners here in California, one of them being the Chabot Space and Science Center in Oakland, one of them being the California Academy of Sciences in San Francisco, and one being the Boys and Girls Club of the Peninsula in East Palo Alto. And we just kicked off a couple weeks ago a 10-week internship program for the Boys and Girls Club. They are spending the first half of their internship learning different science concepts that pertain to the MUSE mission and going on field trips to all of our partners and getting a good idea of what MUSE is all about. In the end, they will produce an outreach product for the MUSE mission, which is very exciting for us. We also have, as of Monday, as of yesterday, a new paper out on our outreach program. Now, if you'd like to scan that QR code, it should bring you straight to that paper, but I believe we also have the link in the chat, or will have the link available for you. That paper is a part of NASA Heat's Heliophysics Big Year special issue for the Frontiers Journal. And we decided to join as a way to introduce the MUSE outreach program because we just got funded in December. So we're a fairly new outreach program, but one I think that carries a lot of value. So what are we talking about? We're talking about the sun, and in order to understand how to observe the sun scientifically and how to extract information out of that, we need to go back to the basics to understand what the sun is. So, the first thing we need to know is that the sun is a star. You may or may not know this. It does not look like the stars in the night sky, but it is because the sun is the closest star to us, the one around which we orbit. Stars are made of plasma. Now that word is used in a lot of different contexts. And so in this context, I don't mean things like biological plasma that lives in your blood. I mean things like astrophysical plasma. And what that means is just gas with an extra electric kick to it. And then, much like myself, the sun is very happily sitting in the middle of its life. And we know that because stars are thermonuclear fusion machines that burn through fuel sources, primarily in the case of the sun, hydrogen. And we're able to guess and refine our estimate of how old the sun is based on its fuel abundances. So let's start from the inside out and learn about what the sun is. The sun's core is fusing currently hydrogen into helium as an energy source. And it is doing that at around the order of 10 million degrees, maybe a little bit hotter sometimes. And some of you may notice that 10 million degrees is usually not hot enough for hydrogen fusion to take place. And so you might be scratching your head a little bit. But in this case, 10 million degrees plus the crushing pressure of the sun's upper layers into the core is enough for hydrogen to fuse into helium. And so that is the sun's main fuel source. Now, the radiation from that fusion has to go somewhere. And we know that because we experience energy from the sun in the form of heat and in the form of light. And so somehow that energy has to propagate through the interior of the sun. And we would like that to happen efficiently and expeditiously. But in reality, this zone right above the core that is called the radiative zone, where the sun is moving energy by way of radiation, it is so turbulent in there that the distance between two particles in that zone is pretty small. And so we've got lots of particle interactions and lots of bouncing off of one another. This is like a great stellar pinball machine, or perhaps traffic in San Francisco, if you want to think about it that way. It is hard for energy to move forward. And it sometimes takes 170,000 years for energy to release itself from the interior to the exterior of the sun. But before that energy moves through the sun, it hits another layer of the sun's interior. And this is where energy transfer, it changes from radiation, moving outward more or less, to convection, where we have circular currents of plasma. We have hotter plasma rising and cooler plasma sinking, and the sun has changed its energy propagation from this radiation to this convection. Now, a very important thing happens at the base of the convection zone and the top of the radiation zone, and that is the sun's magnetic field is generated there. One of the reasons for that is because if we have electric plasma radiating outward and then it hits this shear of convecting plasma, then the plasma is going to rub against one another. And from physics, we know that if we have these changing electric fields, that can generate a magnetic field. Now, the name for this region between the convection zone and the radiation zone is the tachocline. But tachocline is a little bit of a strange word, and to me, it sounds a little bit like taco. And since I'm very food motivated, I usually label it with a taco so that you all know that it's important. So stick a pin in that, and we'll come back to it. Now, the solar surface is a little bit of a selfishly defined thing because the sun's surface glows very brightly in visible light. And so it's light that we can perceive. And so that light is opaque to our eyes. And the surface is littered with evidence of what's happening right underneath. How do we know that the sun has a convection zone and just about how thick it is? Well, we can see things convecting on the surface. Ignore that giant black dot right here and look around that black dot. Do you see that pulsating kind of parcels of plasma boiling around? Well, that is evidence of convecting granules of plasma. Now, you may also notice that, of course, very imposing black spot there in this real observation. This observation was taken actually by one of my colleagues in Norway. He took this at the Swedish Solar Telescope, which of course is located in Spain. And this is an observation of what we call a sunspot. Now, a sunspot is also evidence of the sun's magnetic field. So how do we know that there's convection? We can see it on the surface. How do we know that there's a magnetic field? We can see it on the surface in the form sometimes of sunspots. Now, sunspots are regions of such intense magnetic field that you can maybe imagine a big tube coming right out of that eyeball, sort of towards you. That would be a tube of magnetic flux that is so strong that it actually inhibits the convection underneath it. And if it inhibits the convection, then that means the sun is unable to transfer heat effectively in that region. And so the surface plasma in that sunspot cools down just slightly. And we know from physics that if something is a little bit cooler, then it's a lot darker. So even though it is still hot in there by our measurements, right? Still very hot for a human body, it's a little bit cooler than its surroundings and therefore will look a lot darker. But the majority of the sun is not covered in sunspots because the convection zone is not super thick on the sun. And we have variable numbers of sunspots throughout the sun's life. The majority of the sun's surface is covered by this. This is what we call the quiet sun, not because the magnetic field is non-existent, but because the magnetic field is not strong enough to make a sunspot. It's not strong enough to inhibit that convection that's going on underneath it. So there is still magnetic field, but it doesn't stop that convection. So this is what the majority of the surface looks like. But I can do better. The first layer of the sun's atmosphere, the sun's lower atmosphere, is called the chromosphere. I should go back one, actually, maybe not. The surface is called the photosphere, which means light sphere. But this layer of the atmosphere is called the chromosphere, which means color sphere. This is the first layer of the sun where helium was detected. So Helios, you can imagine. It is also the first layer where we start to perceive the magnetic field in 3D. Magnetic fields are invisible to us. I don't know about you, but when I was a kid in the 90s, we would take these bar magnets and then we would sprinkle little iron filings around the magnet. I'm sure many of you have done this. And to our amazement, the iron filings would take the shape of the magnetic field between the North and South poles. I'll show you a picture of that later. But that essentially illustrates that magnetic fields are lines of magnetic force and they exist even though they are invisible to us. They become visible to us when we have a tracer that is impacted, especially by magnetic fields like iron or like plasma. Plasma loves to stick to magnetic fields, especially in the solar atmosphere where the magnetic field dominates what's going on there. So in this observation, again taken by the Swedish Solar Telescope by my colleague Luke, we can see plasma taking the shape of what very well may be a magnetic loop here. And these little hairy looking things that we call spicules help us understand how turbulent this environment is. This layer of the sun's atmosphere has been described as a burning prairie, and I'm sure you can understand from this observation why that is. But we can do even better here. The sun's upper atmosphere, lovingly known as the corona, because it looks like the sun's beautiful crown. Now, this is an observation taken from space. It is a full disk observation taken by the Solar Dynamics Observatory, and the corona of the sun tends to glow very brightly, especially in extreme ultraviolet light, which is what this is. And we can tell things about what's going on in the sun by looking at what the brightness or the intensity is in this observation. So you may see already a couple of little loops. Of course, this is a 2D projection of a 3D object, so these little loops look like U shapes kind of stuck to the surface, but they're not. They are sticking up. These are magnetic loops. They tend to correlate with where the picture is very bright. The bright points in this picture, in this observation, tell us where the magnetic field is connected, And they tell us where the plasma is very hot. In this wavelength, the plasma bright, or rather the bright plasma there, glows at about 1 million to 1.2 million degrees Kelvin. Now, the dark spots, you may have guessed, are a little bit cooler, right? But they can also tell us something about the magnetic field. It's not necessarily that it's a super weak magnetic field, maybe, but more importantly, the dark regions here are regions where the magnetic field is open to interplanetary space. And since we know that plasma loves to follow magnetic fields, these open magnetic field lines act as a plasma superhighway out into interplanetary space. And these things can launch what's called the solar wind. Now, the solar wind is a constant stream of particles that is always emanating from the sun. But coronal holes tend to give that plasma a little bit of an extra boost, which is what folks who saw the aurora this week would have experienced. That aurora came from a coronal hole. So, what's the issue? Why do I still have funding to do things and think about this? It kind of sounds like we have a lot of the sun more or less figured out, right? Well, what I told you before is that the core of the sun runs at about 10 million degrees. What I did not tell you is that the surface, by the time we get to the surface, the sun has cooled to about 5,000 degrees. 5,000 degrees. Well, that wouldn't be an issue if we weren't finding measurements in the atmosphere of the sun at above 1 million degrees. Recent studies actually suggest 60 million degree plasma, which is crazy. You can't get 60 million degree plasma from a 10 million degree thermonuclear reactor, right? That doesn't make physical sense. This is something that is called the solar coronal heating problem because it is a problem with the way the solar corona is heated. Very descriptive with our problem descriptors. And that means, it implies, that there has to be another source of energy on the sun that is providing this extra energy to the atmosphere. Because those atmospheric temperatures can't be described and can't be explained by simply thermonuclear fusion in the core alone. So what we think, one of the pieces towards solving this problem, is that the sun is transferring some of its magnetic energy into heat and particle acceleration in the atmosphere. And the reason for that, the reason that we think that is because magnetic fields themselves hold intrinsic energy, and that energy can, in fact, be converted through several processes that we observe happening on the sun. Now, first of all, though, how does the sun reflect or express its magnetic energy? Well, the first way is in active regions, what we call an active region. Oftentimes, those regions are rooted in sunspots and they are loops in the corona of magnetic field. But it's also expressed by the quiet sun, where the field isn't as strong, but we still measure million degree plasma above the quiet sun. So that quiet sun looks like this. And a third thing I'm not going to talk about is waves. Waves propagate through the sun and we can measure them using a field of study called helioseismology. So we know that seismology is about usually the study of earthquakes on Earth, but the sun also has earthquakes. So we have helioseismology, sun earthquakes, and these waves propagate at periods that are very regular, and they are magnetoacoustic or magnetic sound waves that move energy from A to B. But the thing that I'm most interested in is quiet sun, because I like a challenge. And we can look at the quiet sun and try to understand the quiet sun using a couple of things, either satellite observations or computer simulations. So I'm going to tell you a story about a computer simulation that had a very happy accident involved with it and led us to discover a couple of nice new things about the sun. So let's rewind to my days in Norway. Norway has a thriving solar physics community in Oslo, And I used to work for them while I was doing my PhD, and they have an in-house computer simulation of the sun's atmosphere called Bifrost. Of course, this is the Viking bridge to Valhalla. Now, this simulation just takes a cube of sun, and that cube, I've shown you a couple of slices through the simulation here. That cube starts at the bottom. In my case, it's about 2,500 kilometers beneath the average solar surface. This next slice here would be essentially the average solar surface. And then these next two slices represent slices through the atmosphere. And I only go about 8,000 kilometers up above the solar surface for this one. So it's a very small cube of sun, but I'm dealing with very small magnetic fields, so I thought it would be fine. Now, what we wanted to do is something that was kind of boring. We wanted to set up a balanced, boring, weak field, vertical field, solar atmosphere where we could get it spun up, because you need to give computer simulations a little time to settle themselves numerically before doing anything weird. And we wanted to then later inject a sheet of just horizontal magnetic field, because what was happening in our simulation is that when we run our simulation for long enough and then we look at the orientation of the magnetic field on the surface, we were finding that our simulated magnetic fields were a lot less horizontal than the observed magnetic fields that are being observed by telescopes in space. So we wanted to see if we could force our simulated magnetic field to be more horizontal by adding horizontal flux, just to see if that's the problem with the simulation or if it's a problem with the observations. But it turns out we didn't get that far because something really strange happened in the middle of what was supposed to be a very boring simulation. What ended up happening and what I ended up noticing after a while, before we even thought about inserting any extra magnetic field into our simulation, I noticed a giant slab of heat in my atmosphere that I didn't put there, that I didn't put anything that should have created that in there. So this became essentially a 3-year mystery solving endeavor to figure out what on earth our simulation did self-consistently to create this big slab of heat. Now, if you want to, oops, sorry, I'm going to go back. If you want to simulate magnetic fields, I'll go back here. You can do a couple of different things. I like to think about simulating magnetic fields as, because the magnetic field, sorry, in this simulation is a free parameter. We get to decide what it is. And if you want to do that, if you want to simulate a magnetic field, I like to think about it as sort of like a pot of spaghetti, basically. If you want to understand how the spaghetti interacts with its watery environment, or how the environment impacts the spaghetti, you can do one of two things. Either you can stick your hand in the pot and move the spaghetti in a very specific direction that you know everything about, and then measure the effect of the spaghetti on its environment. Or you can turn on the boiling and let the spaghetti self-consistently evolve. And that is what our simulation does. And you can see in this slab here that we've got something that sort of looks like that quiet sun observation, right? Because we've turned on the boiling, essentially. We turn on convection in our simulation, and we let the simulation self-consistently evolve. So this big slab of heat was surprising, but clearly self-consistently evolved somehow. And so then my mission was to try and figure out what it was. Now, we know a few things about magnetic fields. But to orient the rest of us, to be on the same page, I need to tell you a couple of facts about magnetic fields. Magnetic fields are extremely picky. We do not observe in nature a magnetic north pole without an immediately adjacent magnetic south pole. We just don't really observe that to happen in the universe. And Magnetic fields are very often compared to electric fields because they coexist quite beautifully in the physics, and the physics works out really well to have them sort of dance together in nature. But this is one way that they differ very significantly from electric fields. With electric fields, we can have positive charges that are free of electric charges and vice versa. You can have a proton that exists without an electron. You can have a free electron. Ideally, someplace in the universe that charge would balance, but this is not how magnets work. We do not observe a north without a south, and so we don't have magnetic monopoles. That's what that's called. Um, Magnetic field lines also hate to cross each other. They will not do it. So in this 2D representation of magnetic field lines not crossing one another, what we have is a blue magnetic system connecting a north to a south, and then a red magnetic system, presumably also connecting a north to a south. And they are getting dangerously close to touching each other and crossing right through one another. But instead, at this interface, when they would have crossed each other, they don't. They do something else. They undergo a process that we call reconnection. And in that process, they essentially switch foot points so that they leave the system as a half red, half blue system, both still connecting a north pole to a south pole, but now they're a completely different system. Okay, why am I telling you this? Well, we know from physics, from Ampere's law, that if the magnetic field changes in space really rapidly, which is exactly what happens at this interface, that generates a lot of electric current over not a lot of space, ergo high current density. And we know that that current density can then dissipate as really intense heat. And on top of that, this rapid change in the magnetic field provides so much energy that it can actually accelerate things, whatever is stuck to it. So, for example, plasma. It can accelerate plasma. So, it could very well be that my big slab of heat, now shown in yellow, is the result of a magnetic reconnection event. Something that I did not prescribe necessarily, but that the simulation self consistently evolved into doing. Now, it took us a really long time to identify the specific magnetic features that created and sustained the energy of this big slab of heat, which created about 1.5 million degree plasma right where it is. But we found them. First of all, we have this blue kind of magnetic arcade here that is entwined with this red, what we call a flux rope. That's kind of a fun term. We have this red magnetic flux rope. And then we have this overlying green field here. This green field happened to be pretty much exactly anti-parallel to the direction of the magnetic field of the flux rope and the arcade. And so when they touched each other, they reconnected so violently that this current generated in between those magnetic features heated up to 1.5 million degrees, and that energy is consistent with what we call a nanoflare. This is a super baby tiny solar flare. So this was pretty spectacular, but we had some questions. Namely, how did these magnetic features come to be? Because we did not put them there. Traditionally, I'll go back just one to look at this red flux rope here. If you want to model a flux rope in the community, usually you will put it in your simulation, already coherently twisted, already a rope. And generally what you do is you stick it underneath the solar surface. This gray slab here is the average solar surface. You would stick it underneath the solar surface, and with your convection, you would allow it to rise by magnetic buoyancy pressure. But we didn't do any of that. So we needed to know what our simulation did to create this magnetic flux rope. And what we found is that our flux rope did not rise through the surface. This is not something that in the community we call flux emergence, or the emergence of magnetic flux through the solar surface. This isn't that. This is a self-consistent ordering of what in the beginning is a very tangled spaghetti mess of magnetic field lines, and through tiny little reconnections becomes a coherent flux rope that eventually holds enough magnetic energy to, upon reconnection, power something like a nanoflare. Now, this goes back to really old magnetic theory that was really difficult for people with idealized models to reproduce. And it is something that we were able to demonstrate through this self-consistent, convectively driven model. So what? There's like 4 people on Earth that care about this, and I'm one of them. So why am I telling you all this, and why am I pulling you through the nitty-gritty of a 3D magnetohydrodynamic simulation? Like, who cares? So the reason this is important is first and foremost that it is really important for us to understand what we're looking at so that we can pull it back into the context of things that Gen Pop cares about. Namely, can we observe it? So now I'm going to pull us back into the realm of satellite observations. Now, one of the cool things that modelers can do is we can make what's called a synthetic observation. That means that we can calculate how much of a certain emission, how much of a certain temperature exists in our little satellite box. If we were to integrate down this way or through the side of the box, how much of a certain temperature exists along that line of sight, and compare that to how sensitive telescopes that we know about are to that specific temperature of light or that specific flavor of light. And this helps us understand whether or not satellites and telescopes that exist or are about to exist would be sensitive enough to the things that we're modeling. Because ultimately, we want a feedback loop between our satellites and our models. We want to improve our models with good data, but we need models to explain what the data can't quite explain. Better resolution in the models usually. So what I did was I calculated how much or how intense the brightest points in my simulation were. And then I adjusted that to align with both the resolution and the sensitivity to that light of the MUSE mission. And I saw in those red circles there that MUSE, when it is designed and when it is built, should be sensitive enough to see this little baby nanoflare, which is spectacular because if we look at some of the other instruments that we have already in space, this is part of the Solar Dynamics Observatory. This is called the Atmospheric Imaging Assembly, and this is where some of the pictures, the beautiful pictures of our solar atmosphere that I showed you earlier, they come from the AIA, and they're lovely, but they're the whole sun. So the resolution of AIA is not that good. And so if I had an observation of what I simulated, and I caught that in AIA, well, I'd have a really hard time convincing people that I knew what that was, right? Just the resolution isn't quite there. But MUSE is going to have much higher resolution and good sensitivity too to these types of extreme ultraviolet light. So that helps us argue for the creation of these beautiful, wonderful satellite programs like MUSE, and this is what we have now. Now, MUSE is a satellite that doesn't quite exist yet. This is a cartoon, of course, of the two-tube instrument that we have that is called MUSE. What we have right now, actually, I can give you a little mission update. We're deep in procurement territory and almost finished. There is a one-to-one mock-up of the two-tube assembly done. And we have a lot of the instrumentation already done. We're just waiting on shipping, essentially, to get everything in hand at the Lockheed Martin Solar and Astrophysics Lab. We depend on the Italians to make our mirrors. We depended on the Germans to perfect our spectrograph. This is a truly international project, and we love working with all of our international friends to make this mission a success. So that's where we're at right now. Assembly is on its way, which is a very exciting phase for missions to be in. So what does MUSE do? Well, MUSE is the Multi-slit Solar Explorer. So that should give you a tiny idea of what it is built to do. It is built to explore the sun. It will not be in orbit around the sun. It will be in orbit around the Earth, in polar orbit. Because instead of having it orbit the Earth like this, where it is in shadow half of the time because of night, it's going to orbit the Earth like this, so it can always stare at the sun except for during eclipse seasons. MUSE is going to use what's called extreme ultraviolet spectroscopy, or a way to extract the fingerprints of UV light in order to figure out what the physics of the solar corona looks like. So this is particularly a corona mission. Now, traditionally, when we want to measure the spectrum or the fingerprint of light, what we do is we force that light through a little slit, and then we disperse that light using usually a diffraction grating into what's called its spectrum. And this is an example spectral line down here. From that spectral line, we can extract the physics out of the signature. Namely, the height of the spectrum gives us an idea of the temperature of the plasma, which is important. The width of the spectral line gives us an idea of the turbulence or the disorder in the plasma, which there always is some because our star is an active star. And in a perfect still world, the spectrum would just be one straight line, no width at all. But we observe width, and that's because the plasma is turbulent. And some of that has to do with the magnetic field as well. And then the shift from center of where we have fine-tuned that spectral line and where we're looking for it, if it's shifted left or right, good news, that means the plasma is moving. That, of course, is excellent news for us because it means that our sun is alive. So that can tell you the relative velocity along the line of sight of what you're seeing. Now, how does this work? I would like to introduce you to Iris. This is MUSE's big sister. Iris is in space and active. It is a 12-year-old mission that is still producing wonderful results and incredible science. This is a real observation from Iris, and Iris is observing a very eruptive event on the sun that we call a coronal mass ejection, something that produces a lot of space weather. It's a lot of plasma that's being released and ejected from the sun. But you may also notice this little dark line in the center of this shifting box, sort of nervously darting up and down. What is that? So that is Iris's spectrograph. Iris was built to be a combination camera and spectrograph, something that measures the spectra of the light. But you may already notice a challenge with the design of Iris here. Now, Iris is doing a really, really good job of scanning what it can scan, but it takes a lot of time to scan. And you see how big that event is? Is Iris possibly able to scan that entire event in space and time and capture the spectral information of the whole thing? Well, no, Iris is a single slit spectrograph. So in cartoon form, what we're getting is light through this one single slit, which then disperses into a line of spectra down that slit, depending on how big our pixel size is and our resolution. And from the information from that spectra, we can invert that into, for example, a line of temperatures. Well, that's great. We now have a little bit of information on what types of spectra give us what types of temperatures, for example, but that doesn't give us much of the big picture, right? That's a challenge. So MUSE is designed to be not a single slit spectrograph, not a double slit spectrograph, but a 35 slit spectrograph. This is a multi-slit solar explorer, right? So in cartoon form, we have light coming through not just one slit, but multiple slits that give us a whole raster of spectra, which we then can invert into a big picture of, for example, temperatures. And then we can sort of see what's going on in the big picture. And in fact, the synthetic observables for MUSE look fantastic. Of course, before we have real data, we need to validate our methods using models. And this far left-hand column here, because I know there's a lot going on, so I'll explain this column by column. This far left-hand column that says simulation, this is what we're using as our ground truth. This is a simulation of an eruptive solar flare. The top row is temperature, and the bottom row is relative velocity. Now, single slit spectrometers in the four boxes on the right-hand side here. They can scan as fast as they possibly can, and they still are only able to get sort of a smeared out version of what that flare is and was, and what that eruption is and was, because it's only that one slit and it takes time to scan the event. But MUSE in this second column here doesn't have to scan the entire region. It just has to scan the distance between two slits. And then you get spectral information from the entire field of view. And so you can see that using a multi-slit approach allows us to extract the physics out of these insanely fast and eruptive events and still get a good space-time evolution of the full event. And this is what we're looking forward to with MUSE. Why do we need that in the first place? Well, we don't have in this way physics of the solar corona that informs how these eruptions happen. And these eruptions affect not only the solar environment, but they affect the Earth environment too. Like, yes, we want a deeper understanding of the sun. Yes, we want to know how to better develop future instruments. A great story is the Iris to MUSE pipeline. And yes, we want tighter constraints on our science models because we want to be able to answer these questions for ourselves and our own understanding. But there's a very real safety concern with things like solar flares and coronal mass ejections. These events can propagate through interplanetary space, and they can cause disturbances in our magnetic field on Earth and our atmosphere on Earth. They tend to scramble GPS positioning signals to the point where a lot of folks can't trust their GPS signals. Now, this isn't super important for us if we're trying to find our way to the grocery store or whatever. Our GPS is going to be sort of okay for that. But if you rely on centimeter accuracy, if you are a shipping company, if you are a farmer, and your GPS position is scrambled by a space weather event, that can affect your business. It can affect your livelihood. Another thing that can happen is these space weather events can induce currents in the Earth, and that can damage our power grid. We've had power blackouts associated with large solar events because of those induced currents in the Earth. These extra currents also exist in the atmosphere. They thicken the atmosphere a little bit, make it a little bit soupy, and that makes it difficult for radio connections to go very far. Not only are there electrons that come matter-wise, but there's also radiation that comes from these events. And the radiation is not safe for human spaceflight. It is not safe for human space exploration. So we need to know and be able to predict when these things are going to come, because we need to tell the astronauts, for example, not to go out of the space station during those events. And if we have a better constraint on how these things happen on the sun because we have better physics because of instruments like MUSE, then our space weather prediction gets a lot better. Another fun kind of extra benefit of studying our sun is that we can also extrapolate to exosolar systems and figure out how other planetary systems deal with the space weather on their star, because the sun can be used sometimes as a solar analog and a stellar analog. And the better we understand the sun, the better we can understand other things in our universe. But I just want to show you a little NASA video of how this process happens. The sun tends to release an energetic event, which creates a shock wave as it propagates through interplanetary space, which impacts our magnetic field. Now remember, this plasma has magnetic properties, and those magnetic properties can reconnect with our magnetic field. That same reconnection process that created my little nanoflare also just happened right there on the night side of our planet. And as those particles are accelerated down our atmosphere, they start interacting with particles in our atmosphere, giving off light signatures that are consistent with the energy that they had to begin with. So not only do we have some real safety concerns, but we also have a lot of really lovely things that happen in our atmosphere because of the sun. And I think a few of you may have experienced this week. These I took on my phone in Fairbanks. We had a pretty nice auroral substorm there. And you can see these different colors. These different colors correspond with different energy levels and different particles that hold that energy. As the solar particles come down into the atmosphere and interact with, namely oxygen and nitrogen particles at different altitudes, holding different intrinsic energies, they then release different colors of light that scales with those energies. And that's what we experience as the northern lights in the northern hemisphere and the southern lights in the southern hemisphere. So not only is it incumbent upon us to understand what the sun is doing for our own safety, but also for our own leisure and our own pleasure, because auroras are so wonderful. And I think I'm just going to leave you with this lovely fisheye video given to me to use by my colleague Jeremy up in Alaska. He and my other colleague Vincent there have teamed up to build these beautiful fisheye cameras called aurora, and you can just leave them out and they capture the most spectacular full sky video of auroras. These videos were taken by both Vincent and Donna up in Canada and Alaska. So these are some of the pleasures that studying the sun leaves us with, and some of the wonderful things that we're looking forward to as the MUSE mission progresses. So thank you very much for joining me. Hope I didn't put you to sleep too quickly. And I hope you have some good questions for me. Thank you for joining.
Oh, Becca, that was just fantastic. Thank you so much, Dr. Robinson. It was a pleasure. I could watch that all day long. Or I guess all night long. Is that the moon there?
This is the moon.
Yeah, that's fantastic. I never thought about the energy levels. It makes me wonder what the aurora would look like in infrared or ultraviolet. I don't
Oh
know.
yeah.
But they're
Yeah.
amazing, right?
Totally amazing. Yeah. Because they're
If
very thermal too. So super strong infrared signals there. There are some auroras that are associated with very strong kinetic waves as well, and they tend to heat up quite a lot. And they are hard to detect if you don't know what you're looking for. So actually, citizen science contributed a lot to us knowing how and in what ways auroral forms present themselves to us in multiple different wavelengths.
That is so cool. Yeah, there are a lot of great Aurora citizen science projects. Maybe we'll throw some of those in the chat. Aurorasaurus. Thanks, Kat. You look like you're on it. I would encourage you all, if you are interested, if you have questions for Dr. Robinson, go ahead and throw those in the Q&A. We have some already that are getting going, and I want to just thank you all for joining us. I'll also ask Kat, there is a survey at the end. We're going to give away one solar toolkit, an extra one if anyone would like to have that for their club or have it for just their own outreach. You're welcome to fill out the survey. Tell us about what you'd like to see next at an upcoming NSN webinar. We're going to put that in the webinar chat for those of you in the Zoom with us. All right, I will start without further ado with some questions we've got. Let's see, is it reasonable to assume that the sun has a coherent overall magnetosphere similar to the Earth's? If so, how does it take shape? Seems like the magnetic fields around the surface of the sun are highly variable locally. And this is from William. I'm curious if they all add up to a greater overall field, or if not, where does the magnetosphere of the sun actually emerge?
That is an excellent question. And the answer is yes, the sun does have an overall, I guess not just global, but solar system scale magnetic field. The way that we decipher and define the boundaries of our solar system is within something that we call the heliosphere. Now, that heliosphere is shaped by the sun's magnetic signature there. So the sun's magnetic field is huge. It extends way beyond the Oort cloud, way beyond what we conceive of the boundaries of our solar system. And that heliosphere is shaped not unlike, as far as we understand it, not unlike the Earth's magnetosphere. Because sort of like the Earth's magnetosphere flopping like a windsock due to the solar wind, the sun is also in relative motion around our galaxy, and it is impacted by that motion and by other fields like the galactic magnetic field, which we also have. And so our perception of the heliospheric magnetic field, or the heliosphere in general, is that it probably looks something very similar to the Earth's magnetic field, squished on one end, flopping on the other end. Now, closer to the sun and where we're likely to perceive the sun's global magnetic field as it is closer to the surface, that is highly variable. About every 11 years or so, the sun's magnetic polarity switches from north up here and south down here to south up here and north down here. And what happens in between is where we are now. This is what we call solar maximum. It's a very interesting time in the sun's magnetic evolution. And that is when the sun's overall magnetic field is less of a poloidal field, kind of like an apple shape, very orderly, and more of a toroidal field, like a donut around the center of the sun. Now, this happens because of a variety of reasons. It happens foremost because of what we call differential rotation. This happens in many different ways on the sun. One way that the sun rotates differentially, because the sun does rotate, it rotates faster along the equator than it does on the poles. And it rotates at different speeds based on how far inside the sun you are as well. So you've got plasma shears on the inside and plasma shears on the outside that happen to drag the magnetic field around the equator faster than in the poles. And that helps move the magnetic field from a polar, poloidal, orderly solar minimum type field, drags it down to these kind of smaller scale eddies that create these smaller scale loops that then interact with one another, where we get a lot of space weather, and we have this toroidal shape. And eventually, though, the field keeps migrating, and it eventually orders out into a poloidal field again. And that happens slowly. It happens because of surface currents. It happens as magnetic flux concentrations move instead of or I guess to the equator, where they cancel and then keep going towards the poles, where they also sometimes cancel if they are the opposite polarity of the pole. So lots and lots of strange things happen with the sun's magnetic cycle, and that is the result of space weather, and it is why we see variations in our space weather where we live closer to the inner heliosphere. So I hope that answers some of that.
That is so cool. Yeah, that actually is a great explanation. This has been a really wonderful presentation altogether. Thank you.
Thank you.
It follow-up question from Carrie that relates to what you were just talking about. They mentioned that an early slide showed magnetic activity on the sun's surface, and that the most intense activity appeared to occur in an area on each side of the equator. And that probably has to do with what you were just talking about, I'm thinking.
Yeah, these kind of low latitude areas during the toroidal field period are usually where most of the action happens. And that is because during the solar cycle, we get magnetic concentrations at like sort of mid to high latitudes that eventually migrate towards the equator. And this happens slowly over the course of 4 or 5 years or so. And so one of the great figures of heliophysics time that I don't have in this talk is called a butterfly diagram. And it sort of maps the latitudes of sunspots throughout solar cycles. And what you see is high to mid latitude sunspots converging to equatorial, and then high to mid latitude sunspots converging to equatorial. So when the sun is in the height of that toroidal active period, we are going to see the majority of that action around the equator or on either side.
Got it. That's really cool. A great question from Vasuki, that what is the connection between solar science and SETI? Why are you at the SETI Institute?
This is such a great question. One of the answers is formal and the other is scientific. Formally, So the outreach program for the MUSE mission is headquartered here because my incredible colleagues Simon Steele and Pamela Harmon wrote the proposal for the MUSE outreach program due to the fact that they are connected so well with not only the Bay Area Ed and Outreach community, but NASA's international and national Ed and Outreach communities. And so essentially, I was dropped into a position that's very well formed for me to kind of kick off and get going. But the other scientific reason why this is now a SETI science is because the sun is the only star that we know of to host life as we understand it. And so understanding more about our solar system is one of the imperatives of SETI science, whether it be biosignatures, so signatures of life as we understand it or life as we can conceive of it, or technosignatures, which is signatures of an advanced society that is able to use and broadcast technology. Both of those things are really important to SETI science, and all of those things happen in our solar system first. And so understanding the sun-Earth connection it turns out to be a really important part of understanding the other aspects of SETI science. So that's why we now have an official heliophysics department at SETI.
That's fantastic. All right, so we're almost at the top of the hour. Maybe just one more question.
Sure.
Let's see, again from William, what mechanism leads to auroras appearing as vertically linear sheets? Why do they appear in that way as opposed to a big mess?
That is a great question. So there are many auroral forms, all of which have very particular physics behind them. However, I will say that in these discrete arcs where you have these vertical sheets and sometimes these like vertical kind of pole structures that happen, that is because under reconnection, remember we talked about how the magnetic field can not only heat up the surrounding plasma, but it can accelerate particles, right? And if solar particles are coming in and being reconnected on the night side of Earth, then they get accelerated down the field lines towards the atmosphere. And so as they gyrosynchrotron radiate down those magnetic field lines, so they spin down the magnetic field lines and start to interact with those particles, what they're doing is they're dumping into the atmosphere, but following that magnetic superhighway all the way down to the auroral oval. So that's why they sort of appear in these vertical sheets. Now, the vertical sheet of color that we perceive is, yes, because of the magnetic field line that is guiding it, but those colors correspond to different altitudes in a layer of our atmosphere that's called the ionosphere. Now, sometimes if it's a certain type of storm with a certain type of energy, or if you're in a certain latitude, usually south of where auroras usually happen, if you catch an aurora, you may notice that they're a little bit red. That's because the red auroras are the highest altitude in the ionosphere. The red auroras correspond to solar electrons that are hitting oxygen that is high up in the ionosphere and releasing that red color based on the energy held by that oxygen. Now, our classic green, this is mid ionosphere. This is a single electron hitting a oxygen and then a secondary electron hitting a nitrogen, if I remember that in the right order. At any rate, it's two reactions that eventually emit this green light. Now, this is easiest for our eyes to see. Our eyes are really good at seeing green. And so even in dark light, auroras are so hard to see. But if we're going to see color, usually the first color we see is green, unless the electrons punch further to the lower ionosphere. And what you get is a layer of low ionospheric molecular nitrogen. That's two nitrogens stuck together. And that energy that it holds is a bright pink. And only during the strongest storms do you get that nitrogen fringe on the bottom of that green sheet. And that's easy to see color-wise too, because storms have to be really strong in order to get that coloration there. And so to summarize all of that, what you're seeing is particles, electrons from the sun, barreling down magnetic field lines as a guide and hitting different particles on the way down in that vertical column.
Oh, wow. Oh, this is just, I have learned more about the sun in the last hour than I feel like I've learned in most of my life. Thank you so much for telling us everything you know, or at least a very tiny bit of that iceberg, I'm sure.
Oh,
Thank
that was it.
much, Becca, for joining us this evening. I want to give a shout out to all of you who also joined us. That'll be it for this evening, and I hope you can join us next month. Wednesday, October 22nd, we'll welcome Dr. Shane Larson, who's going to help us look at our Milky Way galaxy in a whole new way. He's a great speaker as well. If you were at the Astronomical League convention, you may have caught his keynote there, and I was like, please come and talk to us. We'll love you. You can find this webinar along with many others on the Night Sky Network YouTube channel. And I encourage you to go ahead and fill out the survey. If you haven't already, you're welcome to do that. And we'll get back to the person who wins the solar toolkit this week. So thank you all so much. I hope you have a great week and keep looking up. Good night, everyone.
Thank you.
Thank you, Dr. Robinson. Right. I love your talks. I just have so much fun. Thank you so much. You
Thank
got
you.
so
That was
much
so
love in
fun.
the chat. I hope you have seen it. If not, you should save it and save it for a day when you're feeling low because
Oh, I
they
will save it.